Welcome back to the deep dive. This is where we take your sources and really dig in to find those key insights.
Exactly.
And today we're looking at something I find fascinating. How do you get solar power? Well, when the sun isn't shining.
Right, the age-old problem.
Yeah. And the sources pointed towards this hybrid rain solar panel technology. Specifically, its potential in a place you might not expect, North Dakota.
And our mission today is really to understand how this works. Is it just, a cool idea or a real solution? We want to see why North Dakota is such a focus and, well, what the future might look like for getting energy reliably, rain or shine.
Okay, so if you dive right in, how does this magic actually work? Reading through the sources, the concept seemed almost elegantly simple, but how do you get electricity from rain?
Well, it's a clever dual-function design, really. You've got your standard solar cell underneath, as usual.
Okay.
But then on top, there are these two super thin, transparent layers. Think of them like specialized plastic films.
Right, see-through layers.
Exactly. And when raindrops hit that top layer and then roll or slide off,
Yeah.
they create friction between those two layers. It's like rubbing a balloon on your jumper, that static electricity effect.
Ah, okay, I get it.
It's the same principle, basically, called the triboelectric effect. That friction from the moving raindrops generates a real, measurable electric charge.
Wow. And because the layers are see-through?
The sunlight just passes right through to the solar cell underneath, so it's still generating power from the sun at the same time.
So you're getting power from both sources, sun when it's sunny, rain when it's raining.
Precisely. And the sources mentioned some experimental models showing pretty decent results already, peak currents, around 33 nanoamps, voltages near 2.14 volts. Optimized systems might even hit almost 25% efficiency.
That's genuinely innovative. It turns rain from a problem for solar into, well, another power source.
Exactly. It's not just a small bonus. It fundamentally changes the consistency.
Right. Okay, so the tech itself is pretty neat, but why North Dakota? What makes that state such a compelling test case, according to the sources?
Yeah, that's where it gets really interesting. North Dakota's climate is, it's quite varied.
Variable how?
You've got extreme temperature swings. Think below -30 Fahrenheit in winter, up over 100 Fahrenheit in summer.
Wow. Okay.
Plus, they get significant precipitation, maybe 13 to 22 inches a year, but it varies a lot by season. And while they have, around 200 sunny days,
That sounds pretty good, actually.
it is. But the winters often have long stretches of gray, overcast weather. So relying only on sun is tough.
Makes sense.
And add to that, high energy use, especially for heating and cooling, mostly from fossil fuels historically, which means significant CO2 emissions.
So this extreme variability, the existing energy demand, it makes it kind of the perfect storm for testing a hybrid system.
That's exactly what the sources suggest, an ideal testing ground, because this tech is designed for consistent output across different weather conditions.
Okay, it sounds great in theory, but, the real world always comes down to practicality and cost. What did the sources say about that? Is this actually feasible?
That's the million-dollar question, isn't it?
Hmm.
Or rather, the $3 or $4 per watt question.
Ah, so it is more expensive.
Initially, yes.
Mhm.
The estimates put it slightly higher than traditional solar, which is maybe $2.50 to $3.50 per watt.
Okay.
But you're paying for adaptability.
Hmm.
Think about it. Standard solar panels, their efficiency can plummet, like 90 or even 100%, when it's raining heavily.
Right, they basically stop working.
Whereas this hybrid system, well, it keeps generating power from the rain, so the loss is minimal, or it might even produce more overall in mixed conditions.
That trade-off makes sense. And the sources mentioned a real-world example, something about a college.
Yeah, North Dakota State College of Science, NDSCS, they've already put in solar arrays. One example was a 3.5 kilowatt dual-axis tracker system.
Okay, and is that a hybrid system already or just standard solar?
Good question. The sources frame it more as proof that solar in general is practical in North Dakota's climate. It also helps train students, building that workforce.
Right, so it shows solar works there, paving the way perhaps for hybrid tech later.
Exactly. It demonstrates the potential and builds local expertise.
So for the average person in North Dakota, what are the potential upsides here? And realistically, what's stopping this from being everywhere tomorrow? What are the hurdles?
The potential benefits are pretty significant. You're looking at potentially slashing CO2 emissions, maybe 65 to 100% compared to fossil fuels,
That's huge.
and increased energy independence, more reliable power year-round, which is a big deal with those temperature extremes.
Sure. But the challenges?
Well, cost is still a factor. For it to be economically viable right now, Based on the sources, electricity rates need to be around 27 cents per kilowatt hour or higher. That's not the case every.
Okay, so the economics need to align.
Right. And the technology itself, while promising, probably needs more refinement before it's ready for really massive commercial scale-up. And then there's the practical issue of, well, heavy snow in winter potentially covering the panels.
Ah, right. Snow's not rain. Might need special clearing systems or maybe different installation angles like vertical.
Potentially, yeah. Things to be worked out for sure.
So, summing it up, this hybrid rain solar tech it's a really innovative idea. It tackles that core weakness of traditional solar, the lack of sun. It's kind of amazing that simple friction from rain could help power things.
It really is a clever application of physics. And it makes you think, doesn't it? Considering what we've seen about North Dakota's energy needs and its specific climate,
Hmm.
what role could this technology play elsewhere? Especially in regions, all over the world that have really variable weather patterns. As the research improves and we get those costs start coming down, where else could this make a real difference?